components, corresponding frequency components. For example, here F1, F2 are there. Okay, so such that there will be n number of frequency components. Those frequency components will be added up to get this type of waveform. So that's what I have given here. The number of frequency components. See, the noise signal has a high frequency components also. So, but my original signal has a low frequency components. So just by using the low from that waveform or from that time domain waveform, we apply Fourier transform so that we can easily extract the particular bird's sound signal, because each and every bird has a frequency limit. For example, it is like a ball. Whenever you throw a tennis ball, it gets bounced back, right? So same thing, a part of the signal is reflected back and it interferes with the receiver. If that x of t has a finite energy, then you can easily apply the Fourier transform. So the first Dirichlet's condition is that the function x of t can have the... Hello everyone and welcome back to Gyan Mastermind, an exclusive learning platform for electronics and communication engineers for GATE and ESE preparation. Before we start the session, note down the following guidelines. First guideline, use an earphone or headphone for better experience. Second guideline, take notes for better focus and understanding of concepts. Third guideline, do watch till the end of this video for immersive learning of the concepts. The last guideline, leave your questions or comments down below and I will do my best to answer them. Today we will acquire the understanding of the Fourier analysis of signals. Coming to the outcome of today's session, we will be seeing what is Fourier transform and what is the Fourier transform used for, and then comes equation of Fourier transform. So we will understand the Fourier transform and then how the Fourier transform is applied in real-time applications, and finally we will jump into the equation of Fourier transform and understand its equation. Coming to the what is Fourier transform. So consider a time signal. At this point of time, you may be hearing my voice. So my voice is a signal. I am emitting a signal which is of sinusoidal in nature. Not only my voice signal, any signal is composed of sinusoidal. Sinusoidal form is nothing but it is made up of sine components or cosine components. You know what is a sine signal and cosine signal. So my voice is made up of different sine forms and different cosine forms of different frequencies. Okay, so I'm going to emit a number of frequency components and my frequency is limited to a certain frequency. And this signal is represented in time domain. That is, I'm going to measure my voice signal for a continuous time interval, and that is given by this diagram. So the corresponding signal is represented in time domain in this first diagram. The corresponding representation in frequency domain is given by this waveform. And my frequency, as I already told, my frequency, my voice signal, that is my voice signal is limited by a certain frequency. That is given by the bandwidth W. Okay, so my frequency components is limited to the bandwidth W, and this is a waveform. This is another representation of my voice signal, okay, in frequency domain. So this is a time domain waveform and this is a frequency domain waveform. So how you are going to get this frequency details is through use of Fourier transform. Okay, so you are going to get the details of the frequency components using the Fourier transform. So it is a transform and it is a linear operator, because you can transform from time domain to frequency domain representation using Fourier transform, or either you can transform from frequency domain to time domain using inverse frequency transform. Okay, and we use capital letters. This capital A representation is for frequency domain and small or lowercase is used for representing the signal in time domain. And one thing is that my highest frequency for my voice signal is given by W. Next, coming to the second waveform. The second waveform is given by B of t equal to cos 2 pi f1t. Here I have given a time domain representation of a cosine waveform, and it has a single frequency component and the frequency is f1. Let the frequency be f1 and the corresponding waveform in frequency domain is given by this. It has a single frequency component, and it is given by a delta function. Okay, at f1 it has a delta function, and at minus f1 it has another delta function. So this is the frequency domain representation of a given cosine waveform of frequency f1. So this is a single component. There is only a single frequency component, which is unlike the first one. In first diagram, I have given a signal with n number of frequency components. See, in this signal it has a frequency component of f1, and in this waveform you will have a frequency, another frequency, and in this waveform it has another frequency. So those all frequencies are clubbed and the corresponding waveform is given by this. But here, in order to understand how you got this waveform, I have given this waveform, that is a waveform with a single frequency component, and the corresponding frequency domain waveform has a Dirac delta function at frequency f1. Okay. Coming to the next waveform, C of t. So C of t is equal to cos 2 pi f2t. Here I have given a time signal where its frequency is f2, much higher than that of f1. So f2 is higher than that of f1, and the same cosine waveform I have given, and the corresponding waveform in frequency domain is given by the same Dirac delta function at frequency f2, which is much higher than f1. So from this waveform you could easily understand the Fourier transform for a given time signal. Okay. So if you take a n number of sinusoidal signals like this, okay, so if you take n number of sinusoidal signals with different frequency components, those frequency components, corresponding frequency components, for example here f1, f2 are there, okay, so such that there will be n number of frequency components, those frequency components will be added up to get this type of waveform. So that's what I have given here. The signal with the n number of frequency components is given by the waveform, first waveform, and its highest frequency component is given by W. So the frequency components from different sinusoidal signals are added up to form this complex waveform E of f. Coming to the first diagram, here the same thing I have shown here, that is for cosine waveform. The corresponding frequency spectrum C of f is given. It has a single frequency component which is given by a Dirac delta function at f2. Consider a new waveform which is given by sine 2 pi f2t, which has the same frequency as that of the cosine waveform, but here it is a sine waveform which crosses the origin and is measured for a continuous time interval. So let's see what is the Fourier transform for this sinusoidal signal which is sine 2 pi f2t. So it has the same waveform like that of the previous cosine waveform. See, it has the Dirac delta function at the same frequency f2 and minus f2 and negative frequency. But how will you determine if you take a inverse Fourier transform of this one should give the corresponding waveform in time domain? Since these two waveforms are similar, my question is, how will you determine the corresponding waveform in time domain by taking inverse Fourier transform? So there comes the phase representation. I already said that d of f is a complex one. So the magnitude of the complex waveform is given by the mod of d of f, and the magnitudes will be same for cosine as well as the sine waveform, but the phase differs. See, it has a negative minus pi by 2 at f2 and pi by 2 at minus f2. So how do you get this waveform? We will see in detail in the next slide. So from Euler's formula, you know that cos theta equal to 1 by 2 e power j theta plus e power minus j theta. And you know that the cos theta, there is no phase, that is the phase is 0 degree. And by taking the case of sin theta, you have 1 by 2j e power j theta minus e power minus j theta. E is an exponential function. So the small d of t is what you saw in this diagram. This is d of t is sine 2 pi f2t. That's what I have given, and that is given by 1 by 2j e power j 2 pi f2t minus e power minus j 2 pi f2t. And when you take the Fourier transform, it is given by the capital representation d of f. And if you see the cos and sine signal, this is C of f is the frequency domain representation of a cos waveform, and d of f is a frequency representation of a sine waveform. When you take the magnitude, you can see both the magnitudes are equal. But when you take the phase, that is, the angle of d of f is nothing but the phase of the complex waveform d of f. The frequency spectrum which I have shown is a complex thing. It is a real number. It has both magnitude as well as phase. So d of f is nothing but the frequency transform of sine 2 pi f2t, and which is given by the j.5 del of f plus f2 minus j of 0.5 del of f minus f2. So how did you get this del function? It is a Dirac delta function. When you take Fourier transform of a sine signal, you will get a Dirac delta function like this. We will see in detail by calculating. When we go mathematically using the equation, you can easily understand how you got this equation. As of now, just understand the concept. So the phase angle is given by the tan inverse of imaginary divided by real part. So tan inverse of 0.5. So this has an imaginary, right? So this is an imaginary and there is no real part, which implies that tan inverse of infinity is pi by 2. So at f is equal to minus f2, you will get a phase of pi by 2, and at frequency f2, you will get a phase angle of minus pi by 2. So that's what I have given in this diagram. So below in this diagram, I have given the phase spectrum. So phase spectrum plays an important role in determining the actual time domain signal. So what is Fourier transform? You have understood. What is the Fourier transform used for? And we are going to see some of the applications of Fourier transform in real time. For example, consider this noise suppression using filters, and image and video compression, and signal extraction, channel estimation, transmit signal generation. So there are n number of applications where you are going to use Fourier transform just to collect the information about a signal. Because in order to understand a signal, you not only need the time domain values, but you should know what are the frequencies also, frequency related components also. So in order to study the signal, you need both time domain representation as well as the frequency domain representation, so that you can do whatever thing you want to do for that signal. Coming to the first application, noise suppression using filters. So in this application, consider this original signal. So consider my voice signal itself. So this is my voice signal, and when I am going to transmit, it would have mixed up with some noise. So this is an example for a noised signal. The second waveform represents the noised signal, and first waveform is the original signal. So how do I extract this original signal? So in this noise signal, the noise signal as well as my original signal is in this second waveform. So how do I extract the original message signal? So for that, I'm just going to transform my original signal to Fourier transform using Fourier transform. Using Fourier transform, I'm just going to represent my signal in frequency domain, and also the same Fourier transform is applied for this noised signal, which has a number of frequency components. See, the noised signal has a high frequency components also. So, but my original signal has a low frequency components. So just by using the low pass filter. So what is low pass filter? A low pass filter is a filter which filters out the high frequency components and send only the low frequency components. So I'm just using the LPF and just extracting the original signal. That is, I'm going to reconstruct the original signal using LPF. So this is the one of the applications of Fourier transform. Going to the next application, image and video compression. Yes, for image as well as video compression, we use the Fourier transform, that is discrete cosine transform. This is a block diagram for the image and video compression. Here the image is transformed using discrete cosine transform and then done quantization and then encoding, which will bring the JPEG version of that image. That is, here you are going to compress an image which is followed. These are the steps followed to get the JPEG image. So for this transformation, we are going to use the same Fourier transform, and the DCT is nothing but a part of the Fourier transform. So this is another application for the Fourier transform. Signal extraction. See, in forest you could have seen a number of sound acoustic sensors hanged on the trees. So these devices are used to record the sounds of animals, not only animals, as well as the birds. Okay, they are used to record the sounds of birds because they need to understand the ecology of the forest, how the behavior of the birds, not only the behavior and also the ecology, whether a bird's, when does that bird comes into the forest or when does it leaves. For this, they are going to measure or they are going to record these sounds in their devices. So at a time, many birds would be chirping, right? So in order to extract the single sound of a bird or a sound of a single bird from that waveform or from that time domain waveform, we apply Fourier transform so that we can easily extract the particular bird's sound signal, because each and every bird has a frequency limit. For example, if you consider the bat, it would be the frequency, the highest frequency it is emitting would be 1000 kilohertz. And if you consider eagle, it would be of the frequency limit would be of 50 kilohertz. So from this, you can easily understand the importance of the frequency domain representation that is got by the Fourier transform. Consider a bridge step. So the Fourier transform is used to estimate the channel also. So what is bridge step? Consider a DSL, okay, ADSL, asymmetric digital subscriber loop. So this is a thing which is used for telephone connections as well as the broadband connections. So whenever the transmitter, so consider the transmitter as a central office and receiver as your home. The signal from the transmitter travels through this DSL, ADSL and reaches your home, and if you see the signal strength gradually reduces at your home. You should get the same signal, right, as that of the transmitter. So the transmitter signal strength should be same as that the receiver side, but it gets attenuated. Why this is that in the middle, the telephone operators will be providing a bridge step. Bridge step is a provision used for future use. So in future, your locality may demand the same broadband connection, right? So in order to meet the future connections or future lay of the connections, they use the bridge step. The bridge step is nothing but a long copper cable which would be left open circuited. So whenever the signal from the transmitter goes to the receiver, a part of which is go to the bridge step. So from that bridge step, it gets reflected. The bridge step is more like an open circuited and it is like a wall. Whenever you throw a tennis ball, it gets bounced back, right? So same thing, a part of the signal is reflected back and it interferes with the receiver side signal as well as the transmitter side signal. And also, if you see this blue signal, it is the reflected signal and it is out of phase when compared to the received signal, and it gets clubbed and it attenuates the transmitted signal strength. So that's why you are getting the attenuation here, that is the signal strength will be poor at your home. So in order to study about this reflection, we use the Fourier transform to analyze the frequency components of bridge step, that is the reflected wave from the bridge step, and we can totally reduce it. Okay, that is of importance here. So Fourier transform is used to estimate the channel also. So this is one of the applications. Transmit signal generation. Yes, Fourier transform is used to generate the signals also. Till now we have seen that Fourier transform is used for analyzing the signal using the frequency components. But here in OFDM, the Fourier transform is used to generate the signals. Okay, if you consider OFDM, here a number of subcarriers are generated at the transmitter side. That is subcarrier signals which is orthogonal to each other. So these signals are generated using the inverse fast Fourier transform. So that is nothing but the Fourier transform and which is the base. This OFDM is the base for the 5G network. So here, not only the Fourier transform is going to analyze, it is not only used for analyzing the signal, it is also used to generate the signals in case of 5G networks. So these are the applications of Fourier transform. Coming to the equation of Fourier transform. The capital X represents the signal in Fourier transform, which is given by the continuous integral, that is minus infinity to infinity x of t. X of t is the time domain signal multiplied by an exponential function. This exponential function whose term is minus j 2 pi ft. Okay, so exponential function is given by an exponential series which is given by exponential of j theta equal to 1 plus j theta by 1 factorial, and this series goes on like this. Okay, it is an infinite series. So this term is included in this Fourier transform. So this is exponential function is nothing but it comes under unit circle, and it is the Euler's formula. We know that exponential of minus j theta or exponential of j theta is given by sine of cos theta plus j sin theta, which is nothing but e power j theta. These two are same, and we are going to use that in the Fourier transform equation, and where j is given by root of minus 1 and f is the frequency measured in hertz and t is the time measured in seconds, and the x of t is the original signal in time domain representation, and this is a continuous integral. Okay, so this is x of f is a continuous waveform or continuous spectrum that you have to note it down. This is the equation of inverse Fourier transform. X of t is the original signal. So how do you get the original signal in time domain? Is by taking an integral minus infinity to infinity x of f. X of f is the frequency spectrum of the original signal x of t. So x of f is represented as uppercase, and in time domain representation we use lowercase, and it is multiplied by an exponential function of j 2 pi ft, and this integral is also continuous for various frequency components. By multiplying the frequency spectrum with the corresponding exponential function for various frequencies from minus infinity to infinity, you will get back the original signal in time domain. So the x of t and x of f both forms the Fourier transform pair. This is what I've given in the diagrammatic representation in block diagram. G of t time domain, when you take the frequency or the Fourier transform of a time domain signal, you will get the corresponding frequency spectrum which is given by capital G of f. When you take inverse Fourier transform of the frequency spectrum capital G of f, you will get back the time domain signal. So hence it implies that the Fourier transform is a linear operator. You can get back the original signal even after using the transform. Dirichlet's condition. What is Dirichlet's condition? See, for applying Fourier transform, the time domain signal must satisfy some conditions. Okay, those conditions, 3 conditions are given here. These 3 conditions are nothing but that the basic thing is that the time domain signal, if the time domain signal x of t is physically realizable, or if the energy of that time domain signal is less than infinity, or it has the finite energy. If that x of t has the finite energy, then you can easily apply the Fourier transform. So the first Dirichlet's condition is that the function x of t can have the finite, if it has only the finite number of maxima or minima in that particular time interval, then you can apply the Fourier transform. Or if it has a finite number of discontinuities, the same thing, maxima and minima is nothing but it has some discontinuities, right? So if it has a finite number of discontinuities in any particular time interval, then you can apply the Fourier transform for that time signal. As well as if you take the absolute integral for that function x of t, and if it is finite, that is less than infinity, then you can apply the Fourier transform. So these three are the Dirichlet's condition, which means that if the condition is that x of t, the time domain signal, is physically realizable, as well as the energy of the signal is less than infinity. If these conditions are met, you can apply the Fourier transform. Hence, in this session, we have seen what is Fourier transform and what is the Fourier transform used for. We have seen different applications, that is real-time applications, where Fourier transform is used, as well as the equation of Fourier transform and also the conditions for applying the Fourier transform. Thank you.
Alright, that's all for the session. So I hope to see you in the next session soon. Thank you all for watching. To stay up to date with the latest videos, make sure to subscribe to the channel by clicking the red button below this video and hit the bell icon. Thank you.